Hi and welcome to another lesson in the branching series. This time we are going to speak about structured branching. Objectives of the lesson. We will learn about the power and the complexity that jump-style branching can bring. I remind you that those are the kind of instructions that we have just learned about. The instructions that allow us to take decisions and maybe create complex loops. We will study a few high-level structured branching constructs and learn how to follow them when branching in our code. We will turn a hard-to-read piece of code into a nice piece of code. This is less about assembly and more about good guidelines for yourself. It is more about being a good programmer than about writing something that works. We already have learned about how to create decisions and loops in our programs, but it is a bit of a bigger challenge writing programs that you can maintain over a long period of time, and also to create programs that other people can read and understand, and maybe even make it fun to read your programs, not the kind of hell that sometimes happen when people write complex assembly programs. The power of branching. Assembly programming gives the programmer much freedom. There are no jump-based branches in modern programming languages. If you come here after learning some kind of a high-level programming language, mostly a modern one, then you've probably never seen this kind of branches, the jump not zero kind of branches. Even the simple jump instruction. It is not something that you usually see in modern programming languages. Actually, sometimes there are these kind of jumps. Maybe, for example, in C and C++, there is the goto directive that allows you to jump to some arbitrary place in the code. However, usually the use of those kinds of directives or operations in high-level programming languages is usually frowned upon. And maybe there is a good reason. It could cause very strange things in your program, and it could usually make it hard to read. Branching is one of the greatest powers you get as an assembly programmer. It is kind of freedom that you cannot find these days in any modern programming language. Assembly is one of the last places where you can actually jump to wherever you want in your code. This is pretty special, but as everything that gives you much power, there is also the other side. As it says in Spider-Man, for example, with great powers comes great responsibility. And this is mostly true. The fact that you are able to branch to wherever you want in your program doesn't actually mean that you must do it. Actually, you should be careful when doing this kind of things. Unstructured use of branching caused great pain in programming languages of the past. In the last decades, programmers had so many problems because of this kind of branching. Modern programming languages removed much of the branching freedom the programmers used to have, and this is mostly to protect the programmer from himself. Many times, new programmers that didn't have much experience just used their power of jumping to jump all over the place, and it made things very difficult. In order to prevent this kind of things, modern programming languages are built in a way that you cannot actually jump to wherever you want. You can only jump in a very few predetermined ways. The curse of branching. Conditional branches are very powerful. However, many jumps could easily create unreadable code. This kind of code is usually referred to as spaghetti code. We've talked a lot about what could happen. Let's take a look at some piece of code. This is a pretty short piece of code I took it as a screenshot from my Vim editor. We can see in the left pane, I tried to create a sketch of the origin of jumps and their destination. We can see, for example, that here, jump below looper can jump to this label, to the looper label, and we can see it in the black line. Another example is this jump go back. If we follow the blue line, we can see that go back label is here. And actually inside this code there are about 4 jumps. We can see that each one of those has a different color. The thing that you can see when you look at this picture is the many intersections between those lines. You can see that every 2 lines here, almost every 2 lines intersect. There are so many intersections. As a rule of thumb, usually when there are many intersections in the branches inside your code, it means that it is going to be hard to read. This is some kind of a rule of thumb. It's not a mathematical rule or something like this, but this is something that you should pay attention to. If there are too many intersections, the alarm bell in your head should go on. You should be careful about it. I want to explain why people call this spaghetti code. Let's look at this picture. Maybe you should take a few seconds to see the similarities between those 2 pictures. Maybe now you can understand what is the problem with the program on the left. It is just like the spaghetti plate on the right. We don't want our code to be like a spaghetti plate. We want our code to be readable and nice to understand. If your code looks like this, you are in trouble. In the future you won't be able to modify it or work on it. It will just turn into dead code that nobody can touch. Let's speak about the solution. During the last few decades, programmers have developed some rules of thumb and conventions to avoid spaghetti code. A few higher level structures of branching were introduced. Let's talk about some examples of those. The first one is conditional execution, which is known for high-level programmers as the if statement. Another example are loops. High-level programmers, for example, are usually familiar with 2 kinds of loops, the for loop and the while loop. Don't worry if you have never learned about any high-level programming language. We are going to learn about these structures and how to implement those in assembly language. Another construct is called exceptions. This one we are not going to talk about right now. However, I just wanted you to know about this. Maybe in the future we are going to speak a bit about this structure. It is a very interesting one. For the most part, the conditional execution and the loops should allow you to do anything you want. There is even some kind of a mathematical proof that only using conditional execution and loops you should be able to do anything. Limiting yourself to using those constructs will give you some advantages. It will make your code readable to other programmers, and it will also help you to avoid spaghetti code. If you follow these guidelines, it will be very hard to write unreadable code. You could write unreadable code, but it won't be as unreadable as the spaghetti code that we have seen earlier, like this one. You don't want to get to this kind of code. The larger your code becomes, the more important it is to use higher level branching structures. When your code is small, one can say that it doesn't really matter because you can't make your code too complex when it is small. However, I recommend you to use the higher level branching structures even when your code is small, just to get used to it. So when you get to writing bigger systems and your code base is going to be larger, you will already be used to writing in higher level branching structures. So it's pretty important. Make sure that you do it. Let's begin with the if-else statement. This is the basic structure of conditional execution, the basic structure of decision that we can use in our program. It is usually about checking some condition, and if it is fulfilled, we do one thing, and if not, we do something else. In the following examples, not only in the if-else statement, but also in the loops that we are going to speak about, we are going to see two kinds of examples, which are going to be exactly the same, just like here. What we can see in the left is not assembly language. This is some kind of pseudocode. It is just used to show my imagination about what the program does. It is just a rough description of what the program is supposed to do. In the right, we can actually see assembly code. Those two are equivalent. Let's take a look at what we see here. In the left, in the pseudocode, we can see that we have this if statement. Actually, we check if EAX is smaller than EDX. If the condition is fulfilled, we are going to run this piece of code. We are going to add 1 to EAX and then store it inside EAX. If the condition is not fulfilled, we are going to decrease EAX by 1 and store the result inside EAX. This is a very simple idea of some kind of algorithm or execution. It doesn't have any deep meaning. This is just an example. I'll remind you that this is not any specific programming language. This is just a rough description of the high-level idea of the program. Let's look at the interpretation of this high-level idea into assembly language. This is how we are actually going to program it. You can see that in the right and in the left we have some colors and they correspond to each other. I tried to space this part so that every line on the left corresponds to the equivalent line on the right. Roughly, you can see that every line on the left should correspond to something on the right. And specifically, the lines with the colors, they are equivalent. In the assembly language part, we can see that the condition of EAX smaller than EDX is checked using those two instructions. Compare EAX, EDX, and then we jump. We use the jump above equal instruction, which is going to jump only if EAX is greater or equal than EDX. This is actually the opposite of the condition here. Why use the opposite condition? Because we jump to the else clause if the opposite condition happens. Even here, we are going to invoke the else clause only if EAX is greater or equal than EDX. We are going to get to the inc instruction only if EAX is smaller than EDX. I remind you that this comparison is unsigned comparison. We have already talked about the two types of comparison, the unsigned and the signed. It is not very relevant here, but I just remind you that this is unsigned comparison. So if EAX is smaller than EDX, we get to this instruction. Now we want to make sure that we don't accidentally do this instruction too, the decrease instruction. We only want to increase EAX in the case of EAX smaller than EDX. Therefore, we have this jump. This jump instruction is going to skip the else clause, the else part. So this jump is going to jump over all of this, all of the else clause, and it will get directly to the end if. In this kind of construct, of if-else construct, there are two parts. The part that happens if the condition is fulfilled, and the part that happens if the condition is not fulfilled. And we want to make sure that those two different parts will not both be executed. Only one of them will be executed, and exactly one. Not zero of them and not both of them. Exactly one of those two clauses is going to be executed. Here the two different clauses are this one, inc EAX and dec EAX. This is a pretty simple piece of code. Some things to note about in this code. Take a look at it for a second. The first thing that you should note about it is that if we want to have two clauses of if and else, then we have to use two branches. We have here the first branch, which is conditional, and the other one, which is unconditional, which is usually used to skip the else clause. If we didn't want to have an else clause, which is possible, maybe we only want to check if EAX is smaller than EDX, and if so, we just do this part, and we don't have the rest of the else clause. If we actually want to do that, then we could use only one jump instruction. We could use only this instruction, the jump above equal, and we could just discard all the part of the code that begins from the jump and ends here at the dec. So if we want to have if and else, we need two jumps, one conditional and one unconditional. But if we only want to have one clause, only the if clause, then we only need one conditional jump. So it depends on what you want to do.